Now we are discussing exponentially weighted averages or moving averages. These are very useful in the optimization methods whenever we are checking an alternative to gradient descent, which works faster than the gradient descent. So what is this exponentially weighted average or moving average? We are taking the temperatures in the London. These are the 1 year temperatures. The first day temperature is 40 degrees Fahrenheit, and the second day temperature is 49 degrees Fahrenheit, and some 180th day temperature is 60 degrees Fahrenheit, 181th day 56 degrees Fahrenheit. Now we are representing that in the Celsius. So 4 degrees Celsius, 9 degrees Celsius, and 50 degrees Celsius. On the x-axis, we have taken number of days. So 0 to 360. On the y-axis, we have taken the temperature. And you can observe every circle in this graph is representing the temperature of a particular day. With these temperatures, example, if I want to find what is the average temperature of first 10 days, then what is our normal conventional method? We will write the first day temperature and temperature of second day and so on. We will write plus temperature of 10th day and we will do the average by 10. This will give the average of first 10 days temperature. But remember, it is okay if we take the 10 days, and it is okay if we take a little number. If it is a big number, then first we are storing the temperatures, and after that only we are doing the arithmetic operation, the addition. After that we are dividing it by 10. This is okay for the smaller number of data, for example for 10 samples or for 10 temperatures. If the number is incrementing, then we do not want our computer to suffer with the storing of this data. If we have like 1 lakh training samples, or if we want to do the average for 1 lakh values, or if we want to do the average for 1 million values, then instead of storing every value, is there any method which we are calling as moving average? This is an alternative method. In this method also we are trying to find the average, but in a different way we will calculate. We will see how we are calculating. So our motto is we want to find the average temperature. If we want to find the average temperature for first day, second day, or 10th day, or for 50th day, we are expecting example, if we want the 50th up to 50 days average temperature, means all that 50 days average temperature by 50, that is the normal conventional method. Now what we are actually doing, we are discussing now. Initially V0 equal to 0 means what it is telling? The moving average. We are considering the 0th day temperature is 0. Obviously 0th day temperature is 0. Okay, only for calculation purpose we are initializing V0 with the 0. First day temperature, first day average temperature. To calculate a particular day temperature, particular day moving average, we will take the weight. The weight here is 0.9 into previous moving average, that is V0, plus 0.1 into present day temperature. Now if we take V3, V2, it is 0.9 into previous moving average V1 plus 0.1 into present day temperature theta 2. Similarly, Vt is equal to 0.9 into previous moving average, that is Vt minus 1 plus 0.1 into present day temperature. This is how we have to proceed if we want to find the moving average for the n number of days you are expecting. If you are expecting for 50 days, means if you are expecting for 50 days the moving average, then first you have to calculate V0, and then V1, and then V2, and so on, V50. Now we are writing the equation for V50 as it is the weight 0 point some whatever weight we are taking, that is weight into V49 plus the 1 minus the remaining weight. 1 minus 0.9 is 0.1. That 1 minus the weight we have considered into present day temperature. That's how we have to write these equations. Okay. Now let's see what we are actually doing. This is the generalized representation of equation for the exponentially weighted average or moving average. Vt is equal to beta, the weight we are taking, beta into Vt minus 1, previous moving average, plus 1 minus beta into present day temperature. Remember here, theta t is the present day temperature and Vt minus 1 is the previous moving average. So this is depending on previous moving average and present day temperature and beta. So there is a generalized notation Vt equal to 1 minus beta days. What is this? We will see. Example in the previous slide we have seen the beta value as 0.9. If I write 1 minus 0.9, this value is equal to 1 by 0.1. 1 by 0.1 means 10. So if we take beta as 0.9, we can calculate the moving average or exponentially weighted average for 10 days. Or in our example, we can calculate the 10 days average temperature. If we take the beta as 0.9, that means if we want to find the 11 days average temperature, then we should change the weight. So if we are expecting from first day to 10 days average temperature, then first day to 10 days average temperature, then we can use the 0.9 beta. Then 10th day to 20th day, then again we can use the beta as 0.9. 20th day to 30th day, again. So this is first moving average, this is second moving average, this is the third moving average we are getting for 10 days. For 10 days, we can calculate. By calculating the 10 days average temperature, if we plot a graph, that is this red color graph. You can observe here. This red color graph is the exponentially weighted average or moving average we have drawn by considering the beta equal to 0.9. So the changes in this red color graph you are seeing are the changes that are happening for the 10 days. For every 10 days, whatever the changes you are seeing, the changes are represented here. Similarly, if I am changing beta, example, if I am changing beta to 0.98, now this equation has the capability to find the moving average or the exponentially weighted average for the 50 days. Now you can find the temperature of 50 days. How? So if I am taking 1 to 50, so these 50 days temperature, we are taking the 50-day variations and the 50 days average we are representing, and again 50 to 100 we are representing. You can observe this green color line. This green color graph is representing the temperature changes for every 50 days, the average temperature of 50 days. That's why you are seeing a smoother line. Why the line is smoother? Because for 50 days, the temperature may not vary abruptly. So the 50 days temperature, the 50 days temperature graph is compared to the 10 days temperature average graph, it is smoother. In the red color graph, for every 10 days we are taking average. That's why some abrupt changes you are observing. Whereas in the green color graph, we are taking the average for every 50 days. Now, when we are taking the 50 days, beta is 0.98, means 1 point beta is 0.02. So we are neglecting the introduction of a present day temperature. That's why this graph is slightly deviating from everyday temperature. You can observe everyday temperatures are represented by blue circles, but this green color graph is deviating from those blue color circles because the weight for the present day temperature is 0.02 only. Now we are interested in decrementing the beta to 0.05, means now the Vt 1 by 1 minus 0.5 is equal to 2. When the beta equal to 0.5, we are finding the moving average for every 2 days. If we draw the graph by taking beta equal to 0.5, this yellow color graph is giving the average for 2 days. You are observing a abruptions, means changes, very huge changes, because we are taking the average for every 2 days. That's why this graph is, you are seeing a very huge oscillations in the graph. This is how the change in the weight is deciding, the value of beta is deciding how many days it can give the moving average or exponentially weighted average. If we are taking beta value as 0.9, the same equation can give the moving average or exponentially weighted average up to 10 days. If beta value is 0.98, it can give the average up to 50 days. If beta value is 0.5, it can give the average up to only 2 days. Now we have taken this equation, Vt is equal to beta into Vt minus 1 plus 1 minus beta into theta t. For understanding exponentially weighted average well, why the beta value is affecting the number of days, we are taking an example. In this example, I have taken V100 equal to 0.9 into V99 plus 0.1 into theta 100. We already discussed, because the beta is 0.9 here, by using this equation, we can calculate the moving average up to 10 days. Okay. But still, without considering that fact, I am generally taking this equation, and in this equation, I am substituting the V99. What is the V99? It is 0.9 into V98 plus 0.1 into theta 99. So if I substitute V99 in the V100, then we are getting 0.1 into theta 100, that is fine, and 0.9 into 0.1 into theta 99, that is fine, 0.9 square into V98. So 0.1 into theta 100, 0.1 into 0.9 into theta 99. Now, if we substitute V98 in this equation, then and so on, in the V98, if we substitute V97, what is the final equation we are getting? This is the final equation. In this final equation, 0.1 into theta 100, 0.1 into 0.9 into theta 99, 0.1 into 0.9 square theta 98, 0.1 into 0.9 cube theta 97, and so on. So you observe the 0.9 term is rising exponentially, means the 0.9 term you can observe here. Initially it is 0.9 and it is decrementing. It is appearing like this is an exponential decay. So that's why we are calling this as a exponentially weighted average. So now we can observe this in the graph. Remember, after the 0.9 is decaying, we can take n number of terms in this equation. We can write up to V0 also. But 0.9 power 10 is approximately equal to 1 by E, which is almost 0.35. So we are taking this term as almost negligible term. So when the weight is becoming 1 by E, that term is becoming negligible. So even though after we are taking many terms, so theta 100, theta 99, and so on. After theta 91, even though there are terms are existing, theta 90, theta 89, the coefficient of theta 90 is 0.9 power 10. It is very small. So because the coefficient is becoming very small, the remaining terminologies are being neglected. It is like whenever I am taking one fraction, it is like 3.0100000 and so on, some 2 3 4 5 6, some I am writing. Whenever some person asks what is this value, I can say it as a 3.01. This is the equivalent value. Now if another person asks me, tell me the integer value, I say it is 3. It is also equivalent value. Similarly, first we have neglected these points. That is not at all affecting in reality our value. In the second case, we neglected 0.01. That is also not in a big way affecting our original value. Similarly, even though this V100 is the summation of the temperatures of 100 days, the first 10 days weights only predominantly affecting V100. The remaining 90 days weights are not at all affecting, because the coefficients of those temperatures are very small, less than 1 by E. That's why we are saying this V100, this is calculating the 10 days temperature, means from V100 to V90, the 10 days temperature average only. Why? Because the beta is 0.9. That means remaining temperatures are also included in this, but the weights of those days temperatures are very small. That's why we are saying it is calculating only the 10 days temperature, 10 days average temperature, moving average, or exponentially weighted average. We can express the same thing graphically. Remember, we have taken two graphs here. On the first graph, x-axis, we have taken the number of days. On y-axis, we have taken the temperature, day-wise temperature. On the second graph, we have simply taken V100. On y-axis, we have taken the value 0.1. So first I am representing the first expression, 0.1 theta 100. So I am taking the 0.1 here. This is 0.1. I am multiplying. This star is indicating multiplication. Multiplying with theta 100. So 100th day temperature. That's why I am drawing a circle here. So we are multiplying this 0.1 with theta 100. First expression I have represented. Now I am representing the second expression. 0.1 into 0.9. This is the theta 99, means I am drawing an arrow from the theta 99, 99th day temperature, and I am multiplying it with the 0.1 into 0.9. It is the fraction of 0.1, which is 0.9. Second expression also we have represented. Now we are representing the third expression. It is 0.1 into 0.9 square into theta 98. Now this is theta 98. This is 0.1 into 0.9 square. Exponentially it is decaying, you observe. And after 10 samples, if you observe after the 10 samples, the exponentially decay is becoming a minimum value. It is approaching 1 by E. So we can practically neglect those values because the value is becoming very small. 0.9 power 10 is almost becoming 0.35. If you multiply the temperature with the 0.35, it is very smaller value. That's why we are neglecting. That's why we are saying whenever the beta value is 0.9, it can calculate only the 10 days average temperature. If we take the beta value as 0.98, then exponential decay, because the beta is 0.98, 0.98 power 50. At the 50th term, the exponentially it is becoming 1 by E. That's why we are saying if we take the beta as 0.98, the same equation can calculate the moving average up to 50 days. This is how we discussed how the beta, the weight of the equation, is affecting the average. Whenever we are taking the weight difference, if we have taken the weight as 0.9, it is giving the average temperature up to 10 days. If we are taking the weight as 0.98, it is giving the average up to 50 days. If we are taking the weight as 0.5, it is giving the average up to 2 days only. So that's why we are calling this as a exponentially weighted average. Why we are calling as exponentially weighted average? Because whatever the weight we are taking, this weight, whenever the weight's exponential decay is observed until 1 by E, up to that point we can take the average temperature. Now we are interested in representing it as a program. How to write this? So okay, first we have to write V naught equal to 0. Second we have to write V1 is equal to V naught plus 1 minus B into theta 1, and so on we will progress. But whenever we are writing the program, we can directly write it as a V equal to 0, V equal to beta V. Or if you take V theta, then you have to write V theta is equal to beta V theta plus 1 minus beta into theta 1. When we execute as a program in a single line, we can execute. In the first line, we are initiating V theta, and in the loop, we are writing V theta equal to beta V theta plus 1 minus beta into theta t. Here, the previous moving average is updated for every iteration of the loop. Here, the theta t is representing the present day temperature. This is repeated n number of times depending upon our requirement. And remember, we are not storing every value. That's why it is more memory efficient. And our program is very simple. In the single line, we have completed our program. So two advantages. One, our first one is storage is very less, and the second one is our programming became very simple with the implementation of exponentially weighted averages.